Welcome, and I'm very glad to introduce Professor Alexis Deschamps from CMAP Laboratory at University of Grenoble. And Alexis' research is in the area of phase transformation and physical metallurgy in metallic alloys, especially then on the characterization of nanoscale microstructures using large-scale facilities and their relation with properties. And he has pioneered the use of small angle scattering for in situ studies of precipitations. And today he will give us a lecture about mapping the kinetics of phase transformations in compositional space, a tool for alloy design. So please, Alexis.
Well, thanks for this nice introduction. Thank you for the invitation. I'm very, very happy and honored to be part of this prestigious list of speakers that have preceded me in these lectures. I congratulate also the people who have had the ideas to organize this lecture series. I think it's a very good way to try to make a European community of researchers and to build up the feeling of being part of Europe. And I think in these days, it's particularly important, you will all agree. Or at least most people think about that, even though we'll see in France in a few days if a majority thinks this way. Anyway, so today I will talk about the kinetics of phase transformations. I will show first some things about kind of traditional kinetics in a given alloying conditions, and then I will go towards what we've been doing since a few years, which is to try to map the kinetics in compositional space by characterizing compositional gradients. So I'm from Grenoble University. Just a few words about Grenoble for those who don't know. Grenoble is in the middle of the mountains. The campus is somewhere here. Tell me if you don't see the mouse, but I think you do. It's a city which was one of the birth cities of the French Revolution at the castle of Vizille nearby. And more recently, but not so recently, it hosted some Olympic Games in 1968. So it's a mid-sized city and it has a lot of students. About 15% of the population are students. And well, we have many different institutes. Mine is about engineering. And it hosts also some large-scale facilities, in particular the European synchrotron, the SRF, which is a ring here you can see on the picture, and also a pretty large neutron facility, which is ILL, Institut Laue-Langevin, which has a particularity of being a nuclear reactor that you can see here, right close to the middle of the city. I think it's probably one of the few cities in the world where this is the case. Anyway, so the phase transformations, probably most of you know a few things about phase transformations. They can be of different types, depending on the shape of the phase diagram and the way you go through it, especially usually in temperature, but you could go also horizontally if you do diffusion couples. Or you can induce phase changes also by other means as temperature, such as strain and stress. And this helps you to monitor the properties. Just two examples. If you make nanoscale precipitates, these are very efficient obstacles to dislocations, and you can increase, for instance, in aluminum alloys, the yield strength by large amount. And in steels, if you're able to monitor precisely the martensitic transformation of metastable austenite during straining, then you're able to have good combinations of strength and ductility with respect to more traditional grades. So phase diagrams are basically the equilibrium, and they tell you where to go. So when you have a change of temperature, change of thermodynamic conditions, then you look at the phase diagram and it tells you the direction. So where the minimum of energy, where the material wants to go, and this can involve phase transformations. So of course, this equilibrium can be quite far away, and it doesn't mean if you know where to go that you're able to go easily there. So in addition to the equilibrium thermodynamics, you need to know how fast you can go there. And this will involve knowing the diffusion constants of the different species that you need to separate between the different phases that you want to form. And of course, sometimes these classical diffusion constants are not enough. You need to know if you have, for instance, excess vacancies that will increase the kinetics, if you have fast diffusion paths, such as dislocations, moving interfaces, and so on. And so knowing the kinetics of the phase transformation will involve at least these two things, and many others, among which one important point is the presence of activation barriers that can make phase transformations impossible, and that will increase by huge amounts the diversity of phase transformations that you will actually see, just because you want to avoid some of these activation barriers and you try to find some other trajectories to equilibrium. And so to continue on the cycling analogy, this is a typical day of the French Tour de France. And if you're sitting there and you want to go there, so there's a 400 meters difference. So you're going to a point of lower energy. But of course, if you have a huge pass in between, this makes the job a little bit more difficult. And you might want to try to find other ways to overcome this barrier. And so this will have huge effect, especially on nucleation. So just before I go to more detailed analysis of all this, well, I want just to give you two very simple examples about how this can affect the kinetics of phase transformation. So if we take a classical nucleation theory, you can go back to Ernst's lecture on the very much more detailed and that in the yellow lectures. So if you take typical values of the different parameters of this nucleation rate, and you take a 200 millijoule per square meter interfacial energy between the precipitate and the matrix, in these conditions, it gives you an activation barrier of something like 1.5 EV. And this will translate into a nucleation rate of about 10 to the 20 per second per cubic meter. So it means that you will make 100 precipitates, you will nucleate 100 precipitates every second in each micrometer cube, which is a very large amount and which will help you having a very, very dispersed distribution of particles. So if you assume you just multiply by 2 this interfacial energy, then the nucleation barrier is multiplied by 8 because it's as a cube of the interfacial energy, goes to 12 electron volt. And in these conditions of temperature, the nucleation rate becomes 10 to the minus 112. So it means that basically you have 0 particle. Since the Big Bang in the observable universe, you will have less than 1 precipitate. So just to show you how sensitive this precipitation kinetics is to the physical parameters and the necessity to find different ways to have realistic paths and trajectories to transformations. The other example to show you that equilibrium can be far away is a study that was made in 2006 on meteorites. Meteorites that there were calculations showing that they were cooled down from the liquid state at about 1 to 100 degrees Celsius per 1 million year. So it's something where you would expect to be close to equilibrium. And actually during this cooling, it's a steel, basically a steel with nickel and cobalt. And you go through a two-phase, basically intercritical two-phase part of the phase diagram. And of course, then you have a difference of nickel composition between ferrite and austenite. Of course, it's not called ferrite and austenite in this field, but it's basically the same. And actually, if you take this meteorite and you make a composition gradient profile, you can see that you have large composition gradients in each phase, which means that despite this extremely slow cooling rate, you're still quite far from equilibrium. You don't have flat composition profiles. So difficult to get to equilibrium, and then the kinetics is important to understand and characterize. So basically, what do you want to know when you want to understand kinetics? Well, you want to know different parameters of your phases that you're transforming. So this can be geometry, the size, maybe aspect ratio, size distribution. And this can be how much, so volume fraction, number density. And this can be the chemistry, because in many cases, you're not really sure about the chemistry. You can have some substitutions, you can have chemistry evolution during time. And you want to know this also. And of course, if you want to have the kinetics, so it means the evolution with time or with deformation or during deformation and temperature evolution, it's useful to have it in situ to get the full kinetics, except instead of a few points here and there. So this, usually you do that in a single condition. So you do an in situ experiment on one alloy at one temperature, and then you're doing another alloy at another temperature during one straining condition. And then you add up the experiments, and it can be quite long. So what we've been trying to develop is a way to do that in a kind of combinatorial way, to do that not on single arrays, but on gradients of chemical compositions. And gradients could be of composition, but could be on the other parameters as well. And so when you get this data in situ and maybe on combinatorial data, if you're lucky, then you can try to understand the alloy kinetics in alloy design space. So alloy design space is a space of chemical compositions that you can play with, or temperatures, deformation, and so on. And of course, you can use this data to feed models that then can be used for alloy design. So how can you get this quantitative data in situ? Well, I will show example using two different setups. One will be especially for precipitation, nanoscale precipitation. It's using small angle X-ray scattering, which is a very simple experiment where you send X-rays from a source. This can be synchrotron or lab source. It needs to be quite parallel and thin. It goes through your sample, and the light, the X-ray light, is scattered by your precipitates, and you measure the scattering as a function of the angle, and it gives you an intensity profile that you can model and extract some data of the precipitate microstructure. And since you have a bulk sample, it's very easy to do in situ heat treatments. And for more allotropic transformations, consider with a relatively high volume fraction and not too small sizes for the different phases, it's even more simple on the principle, is to do bulk diffraction at high energy. So high energy, it would be something like 100 keV, available mostly at synchrotrons. Which makes it possible to have really a bulk sample, including on relatively heavy materials such as steel or nickel, and collect quite a number of diffraction rings that allow you to have the diffraction profiles, powder diffraction profiles that you can interpret in terms of phase fractions or lattice parameter. So the outline of my talk will be to first to show you a few examples about questions that we are able to answer on using these two techniques, and then we'll go on the combinatorial methodology. So first, a few questions about precipitation. So just for those who are not specialists on small angle scattering, and just a few words about how you extract and what kind of parameters you can extract in situ. This was in a zinc aluminum alloy aged at a relatively low temperature, where you form zinc-rich precipitates in an aluminum matrix. No, aluminum-rich precipitates in a zinc matrix, sorry. And you see that during in situ heating, the scattering signal increases very, very fast, showing the precipitation of sequence. And actually, you can model the full data, but more or less, in this plot, the maximum tells you it's in reciprocal space, such as diffraction. So the position of the maximum tells you the reciprocal of the size of the particles, and the area tells you more or less the volume fraction, if you know the composition of the precipitates. And so when you do that in situ, you can get a very, very precise estimate during time of the size, the volume fraction, and when you know the two, you can evaluate the number density. And so it gives you a full description of a precipitation kinetics in a given set of conditions. We could comment later on in the discussion, if you're interested, why we usually don't see any nucleation stage. So when you do these experiments, you always see a decrease of the density of particles and almost never an increase. But I have no time to discuss this in detail here. So you can go to a bit more complex systems where you have the competitive precipitation of different phases. And one example that I want to show here was in aluminum, copper, lithium, magnesium, where you have the competition between two precipitates, theta prime as platelets and T1 as other platelets. And so this characterization by SAXS with platelets was actually the first application of small angle scattering by André Guigné in 1938. And this was using this technique that he was able to understand why there was a strengthening in duralumin due to the presence of GP zones. So he guessed, looking at these kind of diagrams, the presence of GP zones and was able to determine the size, the diameter, and the thickness of these GP zones. So if you do that in situ, you can see in some conditions here during aging, you have a replacement of theta prime by T1. You still have a few theta prime which are remaining. And the reason for which you can discriminate between the two is that they don't sit on the same habit plates. Theta prime are on 100 and T1s are on 111. And so if I replace this, you can see the evolution of the streaks. The streaks are really the same principle as if you do some light diffraction with a laser by a slit, a Young slit, then you get a streak. And analyzing these streaks, you can get all the parameters of the particles, the thickness of the particles, and their diameter. And you can show, for instance, that the T1s are a single unit cell thick throughout the heat treatment. So they are 1.2, 1.3 nanometer. And the other particles grow in size and the reactivity volume fraction cross each other because you have theta prime, which disappears to the profit of T1. So here, in situ gives you really the kinetics of the transition between two phases, one metastable and one stable. This was another case. It's actually not my research, but from a colleague, Frederick de Gezer, and colleagues in Germany, John Mannhardt and his students. It was something quite similar, but done not on platelets, but on needles and on a single crystal. And this was done with neutrons, because with X-rays, you don't have enough contrast in aluminum, magnesium, silicon. And so these beta double prime particles, which are quite the classical hardening phase for automotive aluminum alloys. They are very sensitive to the prior presence of natural aging. And here, these experiments were done in situ and gave all the parameters of the particles due to the fact that you're in a single crystal and that you can model completely the SAXS signal from these different variants of the precipitates, which gives you this anisotropic signal. And so basically, in situ, you can again get all parameters of non-isotropic particles, the length of double primes, their radius, their volume fraction, and number density, and show indeed that the nucleation is much faster if you don't have natural aging and much slower if you have natural aging. And that this translates also in differences in radius and length of the particles. Now, these X-ray methods, one of the big advantages is that these are not microscopy methods. So you're not sensitive really to the internal structure of the metal. And this is particularly useful when you're looking at severely plastically deformed materials, where basically when you're looking at small objects, you don't see anything because the matrix is too deformed and the diffraction conditions are very complicated. And this was the case, for instance, in oxide dispersion steels, which are considered for nuclear applications. And they are strengthened by oxide precipitates of nanometer size. Here, atom probe image, it's really a diameter of a few nanometers that are extremely stable. I think these are, in metallic materials, the most stable nanometric precipitates that you could find. And actually, to form these oxide precipitates, you have to go through mechanical alloying and to dissolve yttrium, titanium, and oxygen within your stainless steel. And after that, the process goes to annealing and then hot extrusion or hot isostatic pressing. And it's during these steps of annealing and hot deformation that you form these precipitates. But really, it's very difficult to characterize when this happens. What is the kinetics? Do you have any coarsening of these particles? And what is the stoichiometry of these very, very small particles? Which there is always a debate between two different phases, the pyrochlore phase and the Y2TO5 phase. So what we did was to cold press the powders from mechanical alloying, which gives you access to cold press materials that you can handle. And then you can go through it with small X-ray scattering and measure through the thermal treatment the kinetics of precipitation within these powders. And then you get really interesting findings. The first one is that when you heat, let's look at this 14 chromium ODS steel. So 14 chromium is basically a steel that remains ferritic at any temperature during the process. Then initially you have some clusters that you can also image by atom probe. And right from about 500 degrees, you see that precipitates are forming from these clusters and growing, well, relatively fast until you get to 1100 degrees Celsius. At 1100 degrees Celsius, quite interestingly, they stop to grow. And despite the very high temperature, the thermal stability is just amazing. They stay at 1.2 nanometer for more than 1 hour at this temperature. And so this was really the finding of this in-situ kinetics. And if you take another steel grade, which has exactly the same characteristics, except a lower chromium content at 9%, 9% you are going through the gamma loop. So you have this phase transformation between ferrite and austenite during the process. And as soon as you get to the temperature where you have transformed into austenite, then the growth rate of these particles become much faster. And then it stabilizes somewhere around 2 nanometer instead of 1.2. And so this was a direct evidence from the in-situ kinetics that the phase transformation destabilizes the interface between the ODS nanoprecipitates and the matrix. So probably they become incoherent, and then their growth rate is impacted by this change of coherency. Then from small angle scattering, you can get, if you make a hypothesis on the nanoprecipitate composition. So here, if you suppose it's a pyrochlore phase, then you can get the number density. And you can compare this number density with atom probe tips. Of course, they are not in situ. You can't do in situ at 1100 degrees Celsius in an atom probe. And you can compare these number densities. Very interestingly, at the end of the process, you have a perfect agreement between the two. So the SAXS number densities are exactly the same as atom probe, which is quite reassuring. But initially, there is a 1 order of magnitude difference between the two. And we're still not exactly sure where this comes from, but basically it's a sign that the assumption of small angle scattering was wrong, and that these precipitates have not yet reached the full structure, equilibrium structure yet. So to try to understand this in more details, we use a particular technique of X-rays, which is the one possibility offered by synchrotrons is to change continuously the X-ray energy. And when you get close to an absorption edge of one element, for instance here yttrium at 17 keV, then the scattering factor of this element becomes lower. And if you change the scattering factor of this element, it's like changing its number of electrons. And since the intensity you measure is proportional to the contrast of scattering factors, contrast of electronic density between the precipitates and matrix. If you have this element within the precipitates, then by changing the energy, you will see the intensity changing. If, on the other hand, you don't have this element in the precipitates, then the intensity will be the same at the two energies. So really, this anomalous effect helps you to probe the presence of one element within the particles. And when you do that, you can see the difference is quite subtle. You need to make very careful measurements because at two energies, you see a slight change of intensity that you can try to understand. And this, you can try to do in situ during an experiment. So then you can have a chemical information in addition to the structural information continuously during a heat treatment. So here, for these oxide particles, so here it's the heating to 1100 degrees and then holding time isothermal. And you see that the integrated intensity, which is basically the product of the volume fraction times the square of the electronic density difference between precipitate and matrix. So it includes both how many precipitates you have and the contrast between these precipitates and their surroundings. You see that it increases due to volume fraction increase and then decreases necessarily because of a change of contrast. And you always have a difference between the two energies that you probe, one far from the edge in blue and one close to the edge in orange. And this contrast tells you that you have yttrium within the particles. And by knowing the intensity change between these two, you can try to calculate how much with yttrium you have. And so you can do that. You have the in situ data, so a lot of data, a bit noisy because it's very, very small differences between the two intensities. And you can calculate what we call an anomalous factor and compare it to different stoichiometries that you could guess. And actually, at the end of the heat treatment, at the beginning, it varies somehow. At the end, it becomes quite compatible with the two main candidates that you expect, which are the two phases here, Y2TiO5 and Y2TiO2O7. So it's quite good that you end up at this point, but you're not still able to discriminate between the two because basically they have the same yttrium composition, more or less. So now if you want to discriminate between these two phases, you need to act on titanium because they have a factor of 2 in titanium. And so we did some experiments also at the titanium edge, which is more difficult because it's at lower energies. So you need an even thinner sample. And we did that. The first experiments were done at the SRF, the second ones at PSI in Switzerland. And here, the two precipitates are well discriminated. And you can see that you have a kind of an evolution. It was not in situ, it was ex situ, but still, you have a kind of evolution between one phase to another during the heat treatment. So it tells you the transition between two phases that is very difficult to observe by other ways. Okay, so I've tried to show you a few examples of the questions we could answer, both in terms of structure, anisotropy, different parameters of the precipitates, chemistry, and so on. And now I will go to the second part of my talk on more using high energy X-ray diffraction for characterization of more global transformations. And this will be on steels. So the first example I want to show was to try to understand what's happening in Prepersisted magnetic steels. So TRIP is a transformation induced by plasticity. And so it's a transformation during deformation of metastable austenite into martensite. And my PhD student who was working on that made some very nice sketches about the effect of deformation on metastable austenite and the effect of carbon on stabilization of austenite. Of course, if you have more carbon, then the austenite is happier and it's more stable. So if you want to see more of her sketches, you can go on this website. Anyway, the question we wanted to answer was basically how can you master the compromise between austenite fraction and carbon content during these transformations. You want to have as much austenite as possible, as rich as possible in carbon. And this is depending also on the competition between carbon partitioning and carbide formation. So to know that, we could do some in situ X-ray diffraction. So basically, I won't discuss the whole process, but we're looking at the end part here, which is very simple, austenitization, and then isosomal holding at 3 temperatures, 350, 400, 450. And during this isosomal holding, you get some residual austenite that you can characterize at the end at room temperature. But of course, at room temperature, you're not looking at what was happening at higher temperature, because during the final cooling, you can have some martensitic transformation. So that's why you want to know really what's happening during the transformation. So with in situ X-ray diffraction at high energy, you can get a very good time resolution and follow the phase transformations if you have good diffraction conditions and small grain size and so on. We can discuss later on during the discussion the experimental conditions that need to be fulfilled. Anyway, at short times, you can see that the transformation is very fast. It's not too much temperature dependent. And if you go to longer times, the situation becomes more interesting. So at lower austenite fractions and longer times, then you have a crossover between the 3 temperatures. Namely, at low temperature, you have a almost complete transformation, but the residual austenite is very stable. At 450, it's the contrary. You have a stasis at a higher fraction, and then you have a destabilization of the remaining austenite during time. The additional information you can have from the diffraction patterns is the lattice parameter. And during these transformations, the ferrite lattice parameter is more or less constant, and we made the approximation that there was little carbon supersaturation in ferrite in this case. Whereas the austenite lattice parameter is evolving quite a lot. And this is the indication at constant temperature that you have a carbon enrichment. So when you make a carbon balance, if you say I have basically no carbon in ferrite and my carbon is evolving in austenite, I know the austenite fraction. So I know everything about the carbon. Some part is in austenite, and it goes up to about 1.2% at 350, a bit lower at higher temperature. It goes for maximum, which means I have carbon enrichment and then carbon depletion. And if I have this carbon depletion, this is because of carbide formation. And you can get by a difference the carbon content in carbides. And at the end of the day, you can make some maps about how much austenite fraction you can expect with how much carbon content. And so make some different compromises about the amount of austenite you want to reach at which carbon content. And then, of course, you need to take into account what happens during cooling and how much austenite you will keep. To continue on this trip effect, we can see later on it's not on the same material, it's in a duplex stainless steel, but the principle is the same. You can follow what happens during deformation and not so in situ during deformation and not in situ during heat treatment. And the question then is to be able to characterize the phase transformation due to strain and relate that to the mechanical properties and especially the strain hardening rate. And so this system is duplex stainless steels, DSS, and these were more or less at 50%. Well, we tried to have 50% alpha and gamma in 4 different materials, but by playing especially on the nitrogen content to have a different stability of the austenite, which means a different stability with respect to deformation. So in alloy A here, it's very stable. You have the phase fraction in situ measured by X-ray diffraction is constant with strain. Whereas in alloy D, you have almost a full transformation of the austenite in martensite. And in alloys B and C, it's kind of intermediate. And now, if you relate these measurements in situ with the mechanical properties, well, as you expect in the stable alloy where you have no transformation, the austenite is stable, there is no martensite forming, then you have a classical decrease of strain hardening rate with increase of stress. And when you get to the considered criterion, the two equal, then you have ductile failure. When you go to alloy D, the situation is slightly better. You have a fast transformation of martensite, and so an increase of strain hardening rate due to this exactly correlated to the fastest transformation rate. But then it's so fast that it saturates, and when it saturates, the strain hardening rate goes down to 0, and then you have considered criterion, and the strain becomes better but not extraordinary. And in the two alloys which are intermediate, actually mastering the kinetics of the martensitic transformation makes it possible. Since it's a bit slower, it happens later on, only after 20% strain. And this is because it's preceded by epsilon martensite formation before you do the actual alpha prime transformation at the intersection between the two series of epsilon martensite. So you're able to keep the strain hardening rate just above the stress for very, very long, and then go to about 45% of deformation before failure. So really, then the kinetics here of the phase transformation helps you to design the strain hardening rate so that it keeps just above sigma, but not too high, because then it's useless to have such a high hardening rate at a point where you're still far from ductile failure. Okay, so now I hope I haven't been too long in this first part. How can we go further to look not at specific conditions, but at quasi-continuous, how can we get a quasi-continuous description of a compositional space in terms of kinetics? So the principle is very simple, is that since X-ray experiments are spatially resolved, so spatially resolved, the classical X-ray beam in a lab experiment is about 1 millimeter. The classical X-ray beam in a synchrotron is about 100 micrometers. Of course, if you want, you can make it smaller, including to sub-micrometer sizes, but it's kind of complicated. So it's spatially, you have spatially resolved experiments. They're relatively fast. They're sometimes below 1 second, and they're in situ. So the idea is just to do them on a gradient and to scan continuously the gradient in front of the X-ray beam to get the transformation rate as a function of time and composition. So the first case that I will show was coming back to these aluminum, copper, lithium alloys that I was talking about just before. The question was, in these alloys, you have very, very complex precipitation trajectories with many different metastable phases that one can form in their interaction with each other. And the most desirable phase that you want to obtain is T1, aluminum 2, copper, lithium. But actually, you can get many others, and this depends, of course, on temperature, deformation, and so on, and on alloy composition. And the question was, what is the influence of magnesium concentration, which does not take part as a major solute element within the precipitates you want to form, but still has an influence on the precipitation trajectory. And then, since you have different trajectories possible, you have bifurcations in compositional space between these different trajectories, which means, are there some specific compositions where you go brutally from one to another trajectory? And of course, if you want to know for which composition you go from one to another trajectory, you need to have a continuous description, because if you make just a few compositions, you're never going to know when you go from one to the other exactly. So how can you do that? You need to make diffusion couples. In aluminum, it's a bit tedious because you have this oxide layer, which makes it a bit difficult to join two materials of different composition. So in this case, we use the linear friction welding to make a solid state welds with a planar interface between two compositions. So here one was with magnesium, the other one without. And then you make a homogenization treatment to get a composition gradient. If you're not ready to wait forever, then you have sometimes some difficulties to get a gradient over a sufficient distance, because with the resolution, the spatial resolution of X-ray experiments, you're not necessarily able to have many data points within a couple of millimeters like here. So you can extend it by rolling, for instance. And after rolling, we got a gradient between 0 and 0.3% of magnesium over almost 10 millimeters. So then you have a very nice microstructure, constant aluminum, copper, lithium, and varying magnesium. Then you can do experiments where you scan continuously this composition gradient during time. And we did that first at room temperature, very simple. It's easy, you don't need a furnace. And to study the effect of magnesium on clustering of copper. So basically, when you look at these systems, you don't see magnesium because it's almost the same number, atomic number as aluminum. So you just see the clustering of copper. And these are very, very small clusters, like 5 angstroms in radius. So they cannot be characterized by many other means as a small angle scattering. And small angle scattering tells you how much of these clusters you have. And when you look at this composition gradient in magnesium, you see that the magnesium concentration does not change much the size, but basically when you go from one composition to another composition, then you have kind of a jump in the cluster kinetics. So the clustering kinetics is quite slow when you have no magnesium, and suddenly it becomes very, very fast. And this happens for quite small amounts of magnesium, actually less than 0.1%. So if you look here, how with aging time, the clustering kinetics depends on magnesium, you see after a while that it becomes fast, more or less, when you have 0.1% magnesium, and it's slow if you have almost no magnesium. And so this was an interesting indirect effect of solute additions, which is that the presence of magnesium induces the clustering of copper. And it's a complex interaction between vacancies, magnesium, and copper. Now we can do the same at a bit higher temperature. So here it's at 155 degrees. And again, you see the same kind of behavior below 0.1%. So this set of curves, you have a very quite slow kinetics. And suddenly, when you get above something like 0.1%, you jump to another set of curves, which are fast kinetics. And if you look with microscopy, not only you have a change in kinetics, but you have also a change of precipitation trajectory. So for the slow kinetics, you're dominated by theta prime, precipitates, and for the fast kinetics, you're dominated by T1s. And then we're able from this change of trajectory to understand that it was related to the formation of precipitates containing magnesium at these locations, which required a critical amount of magnesium. So if you have less magnesium than 0.1%, you don't have enough supersaturation to form this kind of precursor of S phase. And this S phase participates to help nucleation of T1. So it's an indirect effect of a minor solute addition to help nucleation of an equilibrium phase. And you need a critical amount of solute addition to trigger this effect. And this can really only be characterized on a gradient. If you have only 2 or 3 compositions, you will just see by chance some evolution, but not have a full characterization of what happens in compositional space. The last example that I will develop a little bit more is something we've been starting a couple, 3-4 years ago, on the effect of solid drag on austenite to ferrite phase transformation in steels. And this we look with high energy X-ray diffraction. So solid drag is the fact that solute is segregating to the interface between austenite and ferrite during the phase transformation. This can be substitutional species such as chromium here, or carbon, or both in this case. And this solute, while the interface is moving, is exerting a solute drag, and this changes quite a lot the kinetics. So here, for instance, an experimental kinetics of phase transformation in two different conditions on the same steel containing carbon and chromium. And you can model the kinetics only by solute drag if you look at other thermodynamic conditions such as local equilibrium or para-equilibrium. Then you get kinetics which are much faster than the experimental ones. And so the question was, how much does this solute drag depend on alloy composition? And can we get a robust modeling of this solute drag, which would be able to describe a whole set of different compositions? And then you have coupled interactions between solute species. So this could be a coupled interaction between carbon and chromium, and maybe between carbon and different solute species if you are in quaternary or more alloys. So this again involved to make compositional gradients. So here it took us about 2 years to find out how to make a good composition gradient. So I won't discuss all the experimental hurdles that you need to solve. If you're interested, you can look in the papers and we can discuss that afterwards. But basically, you need again to get if you want to make good experiments, to have a millimeter scale composition gradients, a small grain size, of course, no decarburization and so on, and a constant carbon throughout the composition grade. The small grain size is particularly important because it's difficult to get good diffraction conditions. If you want to get quantitative data, really to have powder conditions is absolutely necessary and quite difficult to reach. So it's a very important point. So here, it's the kind of composition profiles we get. So here it was joining two alloys of one with chromium, one with nickel, and you get an interdiffusion composition profile over here 5 millimeters and constant carbon. So then you have a whole set of different steels that you can probe by moving through this composition gradient. So how do you characterize that? For this, we were lucky to have the help from people of Nancy, Guillaume Jandier, Benoît Denant from Insitu Jean Lamour, and to use their beautiful furnace, which is a lamp furnace, which is normally closed. Here it's open just to be able to see. The sample is a cylinder sitting here. It's heated by heating lamps, and actually this part is rotating at about 5 to 10 hertz. And the rotation helps to get powder conditions for diffraction, because then you can probe all orientations. Well, not all, but many orientations. And you can get a quasi-continuous D-by-Shauer rings and have much more quantitative data. And so the rotation is continuous. And then to probe the composition gradient, you just have to scan vertically your sample in front of the X-ray beam. And then you can probe the full composition gradient. And during isothermal intercritical annealing, then you can follow the fraction of phases. So here, for instance, the evolution of ferrite fraction at 2 temperatures. And you get this kind of oscillations because you're oscillating throughout the composition gradient. And here, at the 2 ends of the oscillations, you get the 2 end compositions, carbon nickel-free and 1% nickel in this case. And in between, you have all the phase fractions for the intermediate compositions. So you get a lot of data here. And then you can try to extract the relationship between composition, time, and fraction. And you can get this kind of data, which is a set of many different phase transformation kinetics for all the compositions of here nickel between 0 and 1%. So 0 is here, 1% is here, and time is going left so that you can see the graph. So this is a lot of data in one single experiment that lasts about half an hour. And then you can look already at the plateau values as a function of nickel. So this is not kinetics, this is just the studies. And you can try to model this by solid drag, LENP, or para-equilibrium. And you can actually find the good solid drag parameters to model this data. But of course, you have more than that. You have the full kinetics. And then you can try to adjust to test your models with respect to the full kinetic maps. And here we're showing this in maps of nickel content in Y, time in X, and ferrite fraction in color. And so this is the experimental data. And this is a solid drag model, and these are LENP and PE. And well, the fit is not perfect. It tells you probably that you could improve the model still. It's much better with solid drag than with the other models. So we've been in about 4 days of experiment at DESY in Germany. We were able to do many different cases, 3 temperatures on iron carbon nickel, 2 temperatures on iron carbon manganese. We were looking also at molybdenum, silicon, chromium, and we did even a few quaternary interdiffusion compositions. So these are, I guess, good ways to get a large amount of data that you can fit now with models. And modeling the solid drag gives the possibility to access to thermodynamic parameters, which were here, the effective binding energy between the different elements. So for the different elements, we're able to model the full composition gradients and different temperatures and see how much these effective binding energies depending on the temperature, for instance, and get also the intrinsic segregation energy, which does not depend on the presence of carbon. So this brings me to my conclusions. And first, I wanted to acknowledge 2 colleagues with whom I've been working extensively on these projects: Frédéric de Gezer on precipitation and Hugo on these phase transformations in steels, and the different PhD students that have been participating to the data I've been showing. And so I hope I've been able to show that having quantitative kinetic data during in situ transformations is useful to understand what's going on. For model assessment, finally, I did not show so much how we could use this quantitative data with models. I could have some more examples, but I was running out of time when I was preparing the talk. And that mapping kinetics in compositional space is able to improve model robustness, can evidence when you have bifurcations in mechanisms, especially in phase transformation trajectories, and then can be used as a tool for accelerating alloy design. Thanks a lot.
Many thanks for this very impressive presentation, and it's really nice to see all these, how you can develop or get so much experimental data in such a short time, even if I understand that it's still tedious, of course. I will stop the recording now.